Good morning to one and all. This is the third part of the lecture on Module 1 for CET 203 Fluid Mechanics and Hydraulics for second year civil engineering students of APJ Abdul Kalam Technological University. And today we are going to discuss on the hydrostatic forces on surfaces, that is the forces applied on surfaces by water that is at rest. So if a surface is submerged in water that is at rest, what is the force exerted on the surface by this water? That is what we will be studying in this particular module. So hydrostatic forces on surfaces. Hydrostatic forces are forces applied by static fluids on surfaces. And there are different types of forces that can be applied by fluids on the surface of a body, and they are pressure force. Pressure force is exerted due to the pressure exerted by the fluid. So in the previous lecture, we had discussed about pressure and pressure force. Pressure force is nothing but pressure into the area of cross section on which that particular pressure is acting. So pressure force is one of the forces that is expressed that is exerted by a fluid on a body. Now another type of force that can be exerted by the fluid on a body is the gravitational force. That is, due to the weight of the fluid, it is going to be exerting a force on the body. So these are the two types of forces that can act on a body due to the presence of a fluid above it. So before we proceed further, we should be knowing the definition of certain terms, or we should be knowing the meaning of certain terms, and these terms are total pressure and center of pressure. Now when you think about total pressure, you think it is the total pressure acting on a body, when actually that is not the case. Total pressure is nothing but a misnomer. Misnomer means something that has been named wrongly. So total pressure actually is standing for the total pressure force. So total pressure is the total pressure force exerted by a static fluid on a surface when the fluid comes in contact with it. So even though the term is called total pressure, that actually stands for the total pressure force. Okay, so when we are talking about what is the total pressure exerted on a body, we are actually talking about the total pressure force exerted by the fluid on the body. And so this should be very clear. Total pressure actually stands for the total pressure force exerted by a static fluid on a surface when the fluid comes in contact with it. The next topic is center of pressure. Okay, and one thing to remember is that the total pressure always acts normal to the surface on which it is acting. That is, perpendicular to the surface on which it is acting. Then we move ahead to center of pressure. So center of pressure, we know that center of gravity is the point where the total weight is acting. So, or total weight is assumed to be acting. Similarly, center of pressure is the point which is on which we assume that the total pressure force is acting. So the point on the surface at which the total pressure force is concentrated. Just like center of gravity is for weight, center of pressure is for total pressure force. That's what you should be knowing about center of pressure. Center of pressure is the point at which the whole pressure force of the body is going to be concentrated. Here, if we look at the lamina, a thin lamina means a thin area. So the thin area is going to be submerged into the fluid. Okay, and so we are submerging that thin area into the fluid. Now the water surrounding this particular lamina is going to be exerting a pressure force on this lamina. So I'm going to take this lamina outside and I'm going to show what all are the forces that are going to be acting on the lamina. So this is the lamina, and this is the total pressure force. Like we told earlier, pressure force F always acts perpendicular to the body on which it is acting. So this lamina is vertical, and so the total pressure force is acting horizontal to the particular lamina. This is total pressure force F, and you can see that it is concentrated at a point here. This point is P, okay, and it is known as the center of pressure. This point P is known as the center of pressure. Now, if this point P was actually shown in this three-dimensional figure, this point P would be somewhere over here. This point P would be here. Okay, and the distance of this point P, this is the center of pressure, from the free surface is denoted by the distance h star. The distance of the center of pressure from the free surface is denoted by h star. So we are going to be dealing with 4 different cases here. Case 1, when a plane surface is submerged in the liquid vertically. Case 2, when a plane surface is submerged in a liquid horizontally. Case 3, when a plane surface is submerged in a liquid when it at an incline to the free surface. And case 4, when a curved surface is submerged in the liquid. And for all these 4 cases, we are going to find out the total pressure. That is the total pressure force acting on this plane surface, and the center of pressure, that is the position at which the total pressure force is going to be acting on this plane surface. Before we move forward, I would just like to give you a small mechanics refresher, some things that you have studied in your engineering mechanics class, which will be helpful for you in the derivations that we will be doing further on. If there is a body and it has center of gravity G, which is at a distance of y bar from the x-axis, and we take a small elemental area dA having a thickness of dy and at a distance, general distance of y from the x-axis, then the expressions for centroid and moment of inertia is given thus. Y bar is given by the formula integral y dA divided by integral dA, or integral y dA by A, which means that integral y dA can be substituted as A into y bar, where A is the area of the whole figure. So this integral y dA equal to A y bar is important because this replacement could be done in many of our upcoming derivations. So integral y dA is equal to A y bar is an important step. You have to keep this in mind. Similarly, the formula for moment of inertia about the x-axis would be given by integral y squared dA. Again, something that you have learnt in your first year engineering mechanics. Ix is given by integral y squared dA. This is some of the things that you will have to remember before we move forward for the derivations. So the derivation for total pressure and position of center of pressure for case 1, that is when a plane lamina is submerged vertically inside water. So this is a plane lamina and it is lying outside the water currently, and what we're going to do is we're going to insert it into water vertically. So it is currently now vertically submerged in water. Okay, and we're going to see the forces that are going to be acting on this particular body. Now, if we take the cross-sectional view, that is, we are going to take it, we are going to look at it from the side. Okay, this particular plane lamina, we're going to look at it from the side. Then this would be how it would look. This is the free surface of water, and this particular body is lying below the free surface. Now, we are going to derive the total pressure force that is going to be acting on this particular body. So, first I'll mark the position of center of gravity and center of pressure. Center of gravity is at a distance of h bar from the free surface, and center of pressure is at a distance of h star from the free surface. Now, I will take a small strip or elemental area on this body, and let me call this elemental area as dA. Let the area of this elemental strip be equal to dA. Okay, and the width of or the depth of this particular strip is equal to dH, and it is at a depth of h below the free surface. So these are the things that are going to describe the vertically submerged surface. It has center of gravity G at a distance of h bar from the free surface. It has center of pressure P at a distance of h star from the free surface, and there is an elemental area dA of depth dH at a distance of h from the free surface. So again, explaining it in writing, A be the area of the lamina, G is at h bar below, center of pressure P is at h star below the free surface, elemental area dA at a depth of h below the free surface. Now, we will move on with the derivation. We have defined all the uh, depths and the points inside the particular lamina, and now we are going to move ahead with the derivation. We are going to take the pressure on this particular elemental strip. Now from hydrostatic law we know that pressure below the free surface increases with an amount equal to rho g h. Since the free surface is at atmospheric pressure, the pressure on this particular strip is going to be P atmosphere plus rho gh. Since P atmosphere is taken to be equal to 0, the pressure on this particular strip is going to be simply rho gh. If pressure on this elemental strip is rho gh, then the pressure force on this elemental strip is going to be rho gh into the area of the strip, which is dA. So the pressure force acting on the elemental strip would be rho gh into dA. This is the pressure force acting on the single elemental strip alone. If we want to find out the total pressure force acting on the whole area, we should integrate this quantity. And so the total pressure force on the lamina is given by integral rho gh into dA. Now, rho and g are constants, can be taken outside. So it becomes rho g into integral h dA. Now we know from our mechanics refresher slide that integral y dA is equal to a y bar. So integral h dA can be replaced with a h bar. So rho g integral h dA can be written as rho g into h bar times a, where h bar is the distance of the centroid from the free surface. And so we obtained the total pressure force acting on the lamina as rho g into h bar into a. Now that we have found out the formula for the total pressure force that is acting on the body, we also need to know the position, that is h star. We need to find out an expression for h star, that is the position at which this total pressure force is going to act. Now, let us consider the free surface as an axis OO. So I've marked this OO here. Now what I'm going to do is I've considered this as an axis because I'm going to take moments about this axis. Now we all know that the small force dF, that is the pressure force acting on the small elemental area dA, is given by rho gh into dA. Okay. Now I am going to take the moment of this dF about the OO axis. Moment means force into perpendicular distance. So the perpendicular distance of this area dA from the OO axis is h, and so the moment of dF about the OO axis becomes h into dF. This is the moment about the free surface. So dm is equal to h into df means rho gh into dA. So h into rho gh into dA or rho g h squared times dA. You can see where I'm going with this because integral h squared dA has been, or integral y squared dA is equal to ixx. So integral, I have to integrate it. So this is the moment of the small elemental strip about the OO axis. So if this is the small elemental strips moment about the O axis, I can take millions of strips like this on the area and integrate them to get the total moment of this area A about the OO axis. And so the total moment of the pressure force about the free surface. Okay, so the small df is giving me a moment of rho g h squared into dA. So like that, millions of df will be acting all over the area. So I'm going to add up all the moments and I'm going to sum it up. So the total moment of the total pressure force about the free surface will be integral dm, which is integral rho g h squared times dA. Now rho and g are constant, so rho g can be taken outside. Moment will become equal to rho g integral h squared dA. H squared dA is nothing but the moment of inertia about the O axis. From the mechanics refresher slide, you might remember that integral y squared dA is nothing but Ixx. So integral h squared dA is nothing but IOO. And so I am going to write moment is equal to rho g into IO, which is moment of inertia about the OO axis. Now I'm going to put this as equation 1, because I'm going to find out this total moment in another way. Okay, this I have found out by taking the moment of a small force dF about the O axis and integrating it for the whole area. But I can also find out the moment of acting about the axis OO in another way. And that is what I'm going to do next. Here, instead of considering the small dFs, I know the total pressure force that is going to be acting on the area. Now, according to Varicknon's theorem, the moment of a force about an axis is equal to the sum of the moments of its components about the same axis. Again, flashback into first year's engineering mechanics. That is, if a resultant force is creating a moment about an axis, the same moment can be obtained by adding up the moments of the components of the resultant force about the same axis. So that's what we are going to do. In the previous slide, we had actually added up the moments of the small components of the total pressure force. In this slide, we will be directly taking the moment of the total pressure force about the OO axis. Okay, so we have summed up the moments of the component forces about the free surface. This will be equal to the moment of the net force about the free surface. Now, what is the net force? We have already found out the net force as equal to rho g h bar into A, and it is a pressure force. It is going to be acting at P, and so the distance of the total pressure force from the free surface is going to be equal to h star, and so moment of the total pressure force about the OO axis is nothing but F into H star, or F is rho g H bar into A. So moment is equal to rho g H bar into A into H star. This is another way of taking moment of the total pressure force about the free surface. So initially we added up the moments of the small df's about the O axis and found out the moment as rho g into IO. Now, in another slide, we found out the moment of the net force about the free surface. Now, these are equivalent according to Varicknon's theorem, and so we are going to equate equations 1 and 2. So, equating equations 1 and 2, we will get rho g IO is equal to rho g h bar into A into h star. The common terms can be cancelled off. You will get h star, which is what we are going to be looking for, is equal to IO divided by AH bar. But when it comes to moment of inertia, we always prefer to write moment of inertia about the centroidal axis rather than any common axis. And so I'm going to replace IO by parallel axis theorem. According to parallel axis theorem, IO is going to be IG plus A into H bar squared, where H bar is the distance between the OO axis and the centroidal x-axis. And so IO is going to be given by IG plus AH bar squared according to parallel axis theorem. If I substitute this value in the numerator of H star, I will get H star is equal to IG by AG plus AH bar the whole square divided by AH bar. So I will end up getting H star is equal to IG by AH bar plus H bar, and this is the mathematical expression for the distance of the center of pressure from the free surface. And so, to summarize, the total pressure force for a surface that has been vertically submerged in a liquid is equal to rho g h bar into A, and the position of center of pressure h star is given by Ig divided by AH bar plus h bar, where Ig is the moment of inertia of this plane surface about its centroidal axis parallel to the free surface. So, going through the moment of inertia through the centroidal axis of some common shapes as well as the position of the centroid. This is required for you to carry out or work out problems in plane surfaces submerged in fluid, because Ig is a term that comes in the expression for H star like you saw previously. So this is a rectangle. The here it's mentioned as Ix when actually it is Ig, because the x-axis here is passing through the centroid of the rectangle. So Igx for this rectangle is given by bh cube by 12. Now you might have a doubt. Iy would be given by Igy would be given by b cube h by 12. Now you might have a doubt as to which side has to get cubed when you're taking moment of inertia about a particular axis. Let me help you remember it in this way, that whichever side the axis is cutting, when you take the gx axis, it is cutting h, and so that side will get cubed. So Igx is bh cube by 12, whereas Igy would be b cube h by 12. So this is the centroidal moment of inertia for a rectangle, and the position of centroid would be h by 2 from the base and b by 2 from the side. Another common shape is a triangle. This is an isosceles triangle of base B and height h. The IGX value for an isosceles triangle is BH cube by 36. BH cube by 36 is the IGX value for a isosceles triangle, and the centroid occurs at a height of h by 3 from the base of the triangle. Another common shape, a very common shape, is a circle. The moment of inertia of a circle is same about the gx as well as the gy axis because it's symmetrical about both the axes. It looks similar. Whether you take the x-axis or y-axis, a circle is a circle. It does not change depending on the axis taken. So the moment of inertia of a circle about the igx axis would be the same as the moment of inertia about the igy axis, and it would be equal to pi r raised to 4 divided by 4. Or instead of radius, if I want to use diameter, then it would read igx is equal to pi d raised to 4 by 64. This is a semicircle, usually not a common question for the university exams. However, the igx, that is the axis that is parallel to the base of the semicircle, is given by 0.11 r raised to 4. And the centroid would lie at a distance, here it is mentioned as 0.4244 r. Another easy way to remember this would be 4 r by 3 pi. This distance of the centroid from the base would be 4 r by 3 pi. Let's move on to a problem on a vertically submerged plane surface. Here, a rectangular plane surface is 2 meter wide and 3 meter deep. It lies in a vertical plane in water. Determine the total pressure and center of pressure of the rectangular surface when its upper edge is horizontal, and subdivision A, that upper edge coincides with the water surface, and subdivision B, that upper edge is 2 meters below the water surface. So it's a rectangular surface that is 2 meter wide and 3 meter deep, and it is submerged vertically. So we have to use the formula that we know for vertically submerged surface, which is the total pressure force is given by rho g h bar into A, and the center of pressure h star is given by Ig divided by A h bar plus h bar. So we'll just go through how this problem is done. It's asked to determine the total pressure and center of pressure. Again, mentioning this again over here, even though they've asked total pressure, what we are actually finding out is the total pressure force, because that is how total pressure force is usually mentioned about. It's referred to as total pressure instead of total pressure force. But whenever you see the word total pressure, it stands for total pressure force. So this is the first subdivision. The first subdivision had told us this is a rectangular lamina, 2 meter wide and 3 meter deep, and the center of gravity is h bar at a distance of h bar from the free surface, and center of pressure is at a distance h star from the free surface, and the upper edge is touching the water surface. It coincides with the water surface. And so let's find out the values of all these things. So first thing is h bar. H bar is lying at the center of the rectangular surface. So h bar is the distance of the centroid of the rectangle from the free surface. So since the depth is 3 meter, G would lie at 3 by 2, 1.5 meter. So once you get 1.5 meter, you can also calculate Ig. Ig is given by BH cube. It's IGX that I'm referring to. IGX is 2 into 3 cube divided by 12. I have to cube the depth. So 2 into 3 cube divided by 12 is Ig, and that comes to 4.5 meter raised to 4. If you look at the units of Ig, B h cube by 12, B is meter, h cube is meter cube. So the unit of Ig is meter raised to 4. And we get Ig for this given rectangle as 4.5 meter raised to 4. Now, the total pressure force is given by rho g h bar into A. So when you're talking about rho g h bar into A, rho is the density of the fluid in which this rectangular surface is submerged. It's given that it is lying in water, and so rho is 1000. G is a constant, h bar is 1.5 meter, A is the area of cross section or area of this particular cross section, which is 3 into 2. So the total pressure force can be easily found out, and substituting the known values, we will get the total pressure force as 88,290 Newton or 88.29 kilonewton. Now the next thing that we have to find out is H star. H star is given by Ig divided by H bar plus H bar. Each and every term is known to you. Ig has been calculated. Area is 3 into 2. H bar is 1.5. So substituting the given values, we will get H star is equal to 2 meter. So this is the case when the rectangular surface is coinciding with the free surface. It's coinciding with the free surface. Now they have also asked us another case in the problem, that is what happens when the rectangular surface is 2 meters below the free surface. So we'll look into that next. So here the same figure, but this time the rectangular surface is lying 2 meters below the free surface. So you can see that H bar has increased, H star has increased all by an amount of 2 meter. So just looking at the figure, you can see that H bar is actually just not 1.5, it is equal to 1.5 plus 2. So let me define H bar to you. H bar is the distance of the centroid of the lamina from the free surface. So that is very important. It is the distance of the centroid of the lamina from the free surface. And so it is 2 plus 3 by 2, which is 3.5 meter. So that is the first thing that you should notice. H bar is 3 by 2 plus 2, which is 3.5 meter. So once you got H bar, everything else is the same. Area is 3 into 2, 6 meter squared, and density is 1000. Also, Ig here remains the same because it's the same lamina that we're talking about. The moment of inertia of the lamina does not change depending on the position it occupies below the free surface. It's only dependent on the dimensions of the lamina. So BH cube by 12, 4.5 meter raised to 4 remains the same, like as in the previous case. Now we can find out the total pressure force. F is equal to rho g H bar into A, which will give us 1000 into 9.81 into 3.5 into 3 into 2, where 3.5 is the only change that has happened here because this particular case lamina is lying 2 meters below the free surface. So H bar has increased to 3.5 meter, and that comes to 2,06,010 Newton or 206.01 kilonewton. Now H star is also equally simple. H star is Ig by H bar plus H bar. So when I substitute all the known values, I will get the value of H star in this particular case to be equal to 3.714 meter. So we will head. This is the next problem. Determine the total pressure and on a circular plate of diameter 1.5 meter, which is placed vertically in water in such a way that the top of the plate is 3 meters below the free surface of water. Also find the position of center of pressure. So this time it is a circle. The cross section is having the shape of a circle, and like we know, Ig is known to us for a circle as pi r raised to 4 by 4 or pi d raised to 4 by 64. The diameter is given as 1.5 meter, and it is placed vertically in water, and the top of the plate is said to be 3 meters below the free surface of water. So first thing, we will draw the figure. So this is the figure. The radius is 0.75 meter. The depth of the circular surface below the free surface is 3 meter. H bar is the distance of the centroid from the free surface, and H star is the distance of center of pressure from the free surface. So first we will find out H bar. From the figure it is obvious that H bar is 3.75 meter. Now area is pi r squared, which is pi into 0.75 squared for a circle, and total pressure force is given by rho g A H bar. So we can find that out. Here I've also calculated the Ig directly. It's given by pi d raised to 4 by 64. I can also use pi r raised to 4 by 4. And I found that Ig is equal to 0.2485 meter raised to 4. The dimensions of Ig, do not forget, is meter raised to 4. Now finding out the total pressure, rho g H bar into A, 1000 into 9.81 into 3.75 into pi r squared, and I end up getting 65,003.5125 Newton or 65.003 kilonewton as the total pressure force. If I want to find out H star, I'll simply use Ig by H bar plus H bar. where h bar, ig and a are known to me. And so substituting, I will get the value of h star to be 3.787 meter. Moving ahead, determine the total pressure and center of pressure on an isosceles triangular plate of base 4 meter and altitude 4 meter when it is vertically immersed in an oil of S equal to 0.9. This is important. Base of the plate coincides with the free surface. That is the plate base. The plate is upside down inside water. The base is coinciding with the free surface. And it's not immersed in water this time. It's immersed in an oil of S equal to 0.9, which means rho becomes equal to 900 kilogram per meter cube. Base and height are given. So you can find out the values of Ig, H bar, etc. So first thing, we have to draw the diagram. So this is the diagram. Base is 4 meter, height is 4 meter. G is at a distance of h bar from the free surface and P is at a distance of h star from the free surface. Now finding it out, h bar is 4 by 3 meter because h bar is said to be h by 3. As we discussed, it is at a distance of h by 3 from the water surface. So this is h by 3, which means 4 by 3 is h bar, and Ig can be calculated as bh cube by 36. Again, I had mentioned this in an earlier slide. The center of gravity, the moment of inertia passing through the centroidal axis, centroidal x-axis is bh cube by 36. So b and h are the same, 4. So 4 into 4 cube by 36, I will get 7.11 meter raised to 4. Important unit of Ig is meter raised to 4. So total pressure force is rho g h bar into A. Here rho is 900 because it is immersed in a liquid that is having specific gravity equal to 0.9. It's not immersed in water. Usually the mistakes that students usually make is they directly substitute rho with 1000 without thinking. Just read through the question once and understand that and make sure that the fluid in which the body is immersed is actually water before actually substituting rho to be 1000. Here in this particular question, density is given, specific gravity is given as 0.9, which means density is 900. And so the total pressure force is given by 900 into 9.81 into 4 by 3 into area of an isosceles triangle, half of base into height. So half into 4 into 4. I will end up getting 94,176 Newton or 94.176 kilonewton as the total pressure force acting on this lamina. H star is given by Ig divided by H bar plus H bar. Ig has been found out, area is known to you, H bar is known. Substituting, you will get the value of H star to be 1.996 meter. So the next case, case 2, is when a horizontal plane surface is submerged in liquid. That is, a plane surface that is submerged in liquid is submerged horizontally in it. We just considered case 1 where it was submerged vertically. Now we are going to check what will happen or what is the force that is going to act on it when it's submerged horizontally. So here you have a plane surface and it is a horizontal plane surface. It's lying in the horizontal plane. When we submerge it in water, it looks like this. Now, if we look at the cross-sectional view of this particular figure, this is the cross-sectional view of this horizontal plane surface submerged in fluid. Now, just by visual inspection, we can understand that each and every point on this plate is equidistant from the free surface. That is, they have the same distance from the free surface as they are lying in a horizontal plane below the water surface. And so, for this particular case, center of pressure and center of gravity both are at a distance equal to h bar and h star, which is equal to a distance h, which is the depth of this plate below the free surface. So here h bar, h star and h are going to be equal as each and every point on this plane surface that is horizontally submerged in the fluid is equidistant from the free surface. So from the cross-sectional view, these are the things that we can deduce. H bar and H star are equal and they are equal to the depth H. That is the depth of the surface below the free surface of water. Since the entire area is at an equal depth h below the free surface, we can say that pressure on the plate at any point is equal to rho into g into h. And so the pressure force on the plate would be equal to rho into g into h into a, where h is the depth of the surface below the free surface. So in a horizontal plane surface submerged in liquid, the summary is simple. The h bar, distance of h bar is equal to h star, which is the distance of center of pressure from the free surface, and it is equal to the depth h at which the body is submerged, and therefore the total pressure force can be written as rho gh, which is the pressure at any point on the plate into the area of the plate. Case 3 is when an inclined plane surface is submerged in the liquid. So here you have a plane surface, a thin lamina, which is held at an incline, and now we're going to submerge it into the fluid. So here we have submerged this surface into the fluid, and we can see that the particular surface is actually placed at an incline to the free surface. So this is the cross-sectional view. From the cross-section, we'll only be able to see this edge of the plate, and this is the cross-sectional view of this particular scenario when the plate is submerged at an incline. Now when we're talking about incline, there should be an angle involved, and that angle is theta. Theta is the angle made by the plane surface with the free surface of fluid. If this theta is transferred onto the cross-sectional view, it would look like this. This is the angle made by the plane surface with the inclined plane surface with the free surface of fluid. Okay, so now considering case 3, where is inclined plane surface submerged in liquid, it is important that we determine we know how to locate the center of pressure, center of gravity, etc. for this particular plane lamina. And so on the two-dimensional figure, I'm marking the center of gravity and the center of pressure. Center of gravity and center of pressure when marked on the three-dimensional figure would look like this. So whatever points I'm drawing on the two-dimensional figure, I'm also correspondingly showing that on the three-dimensional figure. Now this is done so that it will help you visualize what we are actually explaining. The distance of center of gravity from the free surface is given to be h bar. If marked in the three-dimensional figure, this is h bar. From the free surface to center of gravity is h bar. Vertical distance from the free surface to the center of gravity is h bar. Similarly, the vertical distance from the free surface to the center of pressure is h star. And here also the distance from the free surface to the center of pressure is h star. Now I'm also going to mark the inclined distances. That is the distances along the plate. This is the vertical distance. I'm also going to mark the distances along the plate. Y bar is the distance up to G along the plate from the free surface. So correspondingly, if I were to mark it in the two-dimensional figure, it would look like this. This is Y bar corresponding to h bar, which is the vertical distance. Y bar is the distance along the plate. Similarly, for center of pressure, the distance along the plate is marked as y star. In the two-dimensional figure, it would look thus. So these are the things that you have to keep in mind. H bar is the vertical distance of center of gravity. H star is the vertical distance of the center of pressure from the free surface. Y bar and Y star are the distances from the free surface to G and P along the plate. Now, from the figure, I'm going to I'm going to make a deduction from this figure. I can see that sine theta, this is the angle theta, sine theta can be written as h bar divided by y bar. It can also be written as h star divided by y star. And so I can write h bar as y bar sine theta and h star as y star sine theta. We have to keep this in mind because we will be requiring the details of this, or we will be requiring this particular relation in our derivations that are going to come up. So h bar is y bar sine theta and h star is y star sine theta. So here now I've got rid of the three-dimensional figure. Instead, this is the surface, the top view of the surface. I've just marked it here in red to help me explain this derivation in a little bit more detail. So this is the cross-sectional view and this is the top view of the plate, the inclined plate. So I'm taking a small element here on the plate which is dA, and it is at a distance of y from the free surface along the plate. If the same thing is shown in the cross-sectional view, in the two-dimensional view, this red strip shows the edge of the small elemental strip, and the vertical distance of this small strip from the free surface is given as h, a general distance h. So the small strip is at a general distance h from vertically from the free surface and a general distance y along the plate. I've just taken a small strip dA at a distance of y along the plate and at a distance of h vertically from the free surface. So considering a small element dA at a depth h from the free surface, the pressure, okay, before that, again, sine theta can also be written as h by y, just like we wrote sine theta to be h bar by y bar and h star by y star. Sine theta can also be written as h by y, and so I can get the relationship h is equal to y sine theta. So h bar is equal to y bar sine theta, h star is equal to y star sine theta, and h is equal to y sine theta are all important relations for us in this derivation. Now, the pressure acting on the element dA would be equal to rho into g into h. This is because h is the vertical distance of this element below the free surface, and any point that is at a depth h below the free surface has a pressure equal to rho gh acting on it, and the expression rho gh can be replaced as rho g into y sine theta, because I know that h is equal to y sine theta. Now, if I found out pressure, I can also find out the pressure force simply by multiplying it with the area on which it is acting. So, the total pressure force acting on dA, which is dF, can be written as rho g y sine theta into dA. And so, the total pressure force acting on the whole lamina can be obtained by integrating this expression as integral rho g y sine theta into dA. All the constant terms can be taken outside. Rho g as well as sine theta is a constant because theta is a constant. So only things remaining inside the integral sign would be y dA, and as we had discussed in the mechanics refresher earlier, integral y dA is nothing but a y bar, and so rho g sine theta into y bar a is what we get as total pressure force on the lamina. But we know that sine theta into y bar or y bar sine theta is nothing but h bar. And so the total pressure force on the lamina is given by rho g h bar into a. So we have ended up with the same expression that we found for vertically submerged surfaces immersed in the fluid. Here, even for inclined surfaces, the total pressure force on the lamina was derived to be rho g into h bar into a. The expression remains the same, where h bar is the vertical distance of the center of gravity from the free surface. Now we need to also find out the position of h star. We need to find out an expression for h star. Here I have marked the pressure force F acting at center of pressure P. Now you must notice the direction in which total pressure force F is acting. It is acting normal to the plate. Okay, it is acting normal at 90 degrees to the plate. So now I am taking the small strip dA, and there is a small pressure force dF acting on it, perpendicular to it. Now if I want to find out dF is nothing but the pressure force acting on the small element dA, and so the small pressure force acting on dF is given by rho gh into dA. H is equal to y sine theta. Now I'm going to take the moment of this small force dF about the OO axis. This is the OO axis. I'm going to take the moment of dF about the OO axis. The distance of the perpendicular distance of dF from the OO axis is y, and so the moment of dF about the OO axis is going to be dF into y. So I will get rho gh into dA into y. but h is y sine theta. I've substituted h is y sine theta over here. So I'll get rho g y sine theta into dA into y. So like this small df, thousands of other dfs will be acting on this plate. Because this small element is can be drawn anywhere here. There are hundreds, thousands or millions of elements on this plate, all of them having a small force df acting on the lamina. And so the moments, the sum of the moments of all these small forces about the OO axis can be obtained by integrating this particular expression. Okay. And so this total moment of all the pressure forces about the OO axis is equal to integral rho g sine theta into y squared dA. So I have summed up the moments of small dfs about the OO axis by integrating them. So all the common terms can be taken, common alla, all the constant terms can be taken outside. So rho g sine theta can be taken outside. So integral y squared dA will remain. Integral y squared dA is nothing but the moment of inertia about the axis about which we are taking the moment, which is the OO axis. So the total moment of all the small pressure forces about OO can be obtained as rho g sine theta into IO. And this is equation number 1. Now I'm following the same procedure here that I followed for vertically submerged surface inside a fluid. Instead of h squared dA, I'm just having y squared dA. And instead of taking moment about the free surface, I'm actually taking it about the OO axis. And so rho g sine theta into IO is the moment of the small pressure forces about the OO axis. Now you know where I'm going with this. I'm going to use Varicknon's theorem. Okay, and I'm going to equate this total moment about of all the small forces about OO axis. I'm going to equate it to the moment of the one and only big force F about the OO axis, because according to Varicknon's theorem, the moment of the net force about an axis is equal to sum of the moments of the components about the same axis. So moment of capital F about OO axis is equal to sum of moments of all these small df's about the OO axis. So I found out the sum of the small df's, moments of the small df's about OO axis to be rho g sine theta into IO. Now I have to find out the moment of F about the OO axis. So moment of the net force F about the OO axis is given by F into y star. Now F, we have already found it to be rho g h bar into A. So moment of net force F about OO axis is rho g h bar into A into y star. Now I am replacing h bar with y bar sine theta. So rho g y bar sine theta into A into y star. This is equation 2. So according to Varicknon's theorem, this is equal to equation 1. Because equation 2 is the moment of the net force F about OO axis, whereas equation 1 was the sum of the moments of all the small forces dF about the OO axis. So according to Varicknon's theorem, moment of net force about an axis equal to sum of the moments of the component forces about the about the same axis. So all the sum of the moments of the small df's about OO axis is equal to rho g y bar sine theta A into y star. So equation 1 can be equated to equation 2. So I'm going to equate them. Equating equations 1 and 2, I will get rho g sine theta into IO is equal to rho g y bar sine theta A into y star. So all the common terms I can cancel out. Rho g sine theta etc. gets cancelled off. I will get IO is equal to y bar A into y star. Now my aim was to find out h star. So I'm going to isolate y star. Okay, before that, I'm going to write IO as Ig plus AY bar squared. This is parallel axis theorem. Moment about any axis is equal to moment about the centroidal axis plus product of area into distance between the two axes, the whole squared. So Ig plus AY bar squared, according to parallel axis theorem, IO is equal to Ig plus AY bar squared, and that is equal to y bar into A into y star. So y star will become Ig by y bar times A plus y bar equal to y star. Now my aim is to find out h star, not y star. H star is the vertical distance of P from the free surface, and I know that h star is equal to y star sine theta. So I am going to replace y bar, y star, etc. with h star and h bar. So Ig divided by h bar by sine theta into a becomes Ig sine theta by h bar a plus h bar by sine theta is equal to h star by sine theta. Taking sine theta to the opposite side, I will get h star is equal to Ig sine squared theta divided by h bar into a plus h bar. So this is the expression for the center of pressure of a inclined plane surface. The center of pressure of an inclined plane surface from the free surface. And now what is important to note is that the expression and how similar it is to the expression for center of pressure of a vertically submerged lamina in a fluid. The only difference is the sine squared theta, where theta is the angle made by the plate with the free surface. So if you look at this expression carefully, you will be able to understand that the case 1, which was vertical plane surface submerged in fluid, is actually a special case of case 3. When a plate is submerged vertically, theta becomes equal to 90. Sine theta becomes equal to 1 and h star will become Ig divided by h bar into a plus h bar. So Ig into sine squared theta divided by h bar a plus h bar is a general expression for h star for any type of plate submerged in fluid, whether it's vertical, horizontal or inclined. If the plate was horizontal, theta would have been 0, sine theta would have been equal to 0, so this term would vanish and h star would become equal to h bar. And so by substituting the different values of theta, you can get the expression for h star for case 1, case 2 as well as case 3. And so that is what makes this derivation a very important derivation, because both case 1 and case 2 are found to be a special case of case 3. Case 3 is the actual derivation, case 1 and case 2 are special cases of the inclined plane surface submerged in liquid. And so for inclined plane surface submerged in liquid, the total pressure is found to be rho g into h bar into a, and h star is found to be Ig sine squared theta divided by h bar into a plus h bar. So let us do a numerical problem. A rectangular plane surface 2 meter wide and 3 meter deep lies in water in such a way that its plane makes an angle of 30 degrees with the free surface of water. The upper edge is 1.5 meter below the free surface. Determine the total pressure and position of center of pressure. So let us first draw the figure. The angle is given. It's an inclined plane surface submerged in liquid. So this is the figure. Now why I have drawn it like this is because it is said that the upper edge is 1.5 meters below the free surface, and so the upper edge does not touch the free surface. So this is the top view of that particular rectangular plate of dimensions 2 meter width and 3 meter depth. And this is the center of pressure and center of gravity for the plate. It is said that the upper edge is 1.5 meters below the free surface and it is inclined at an angle of 30 degrees to the free surface. So all this is included in the figure. So h bar is the vertical distance of center of gravity from the free surface, and h star is the vertical distance of the center of pressure from the free surface. Now from the figure we can understand that the distance up to g is 1.5 meter from the edge of the plate. However, we don't know the total distance. So this much distance is 1.5 meter. It's lying exactly at the center of the plate. Now in order to calculate h bar and h star, we can use the knowledge of simple trigonometry that we might have studied in our 10th standard, which was using sine theta and similar triangles and so on. So what I'm going to do here is that I'm going to mark this particular distance as x. This distance is unknown to me, and from the figure I can figure out that sine 30 is equal to 1.5 by x, which is equal to h bar divided by 1.5 plus x. And so since I know the value of sine 30, I will be able to get the value of x, and after I find out the value of x, I will also be able to find out the value of h bar. And so solving, I will get x is equal to 3 meter, and once I get the value of x, I will be able to get h bar to be 1.5 plus x into sine 30, which is 2.2. 0.25 meter. Now, knowledge of h bar is very important to me because only if I know h bar will I be able to calculate the total pressure force F. So F is given by rho g h bar into A. So on substituting the known values, rho is known, g is known, h bar is known, area is 3 into 2. I will be able to get 1,32,435 Newton or 132.435 kilonewton as the total pressure force on the lamina. Now to find out h star is given by Ig sine squared theta divided by h bar into A plus h bar. Value of h bar is known to me. Ig is the moment of inertia of this particular rectangle passing through the centroid. So it's going to cut the 3 meter side. So Ig is going to be 2 into 3 cube divided by 12. And sine squared theta is sine squared 30. H bar is 2.25 meter and area is 6 meters squared. So on substituting all these values, I will get H star as equal to 2.33 meter. Moving on to the next problem. A circular plate 3 meter in diameter is immersed in water in such a way that its greatest and least depth below the free surface are 4 meter and 1.5 meter respectively. They have asked to determine the total pressure and the position of center of pressure for the plate. Now this question, if you read it once again, now I have included this question as part of inclined plane surface submerged in fluid. However, if you read this question carefully, nowhere is it mentioned that the plate is inclined. I'll read it again. A circular plate 3 meter in diameter is immersed in water in such a way that its greatest and least depth below the free surface are 4 meter and 1.5 meter respectively. Determine the total pressure and position of center of pressure of the plate. So it's not mentioned anywhere that the circular plate is inclined. It could as well be vertical. So you have to read it to understand why this particular plate is inclined. It's said that the diameter of the plate is 3 meter and the greatest and least depth below the free surface are 4 meter and 1.5 meter respectively. So the top surface of the circular plate is 1.5 meter below the free surface. If the circular plate was indeed vertically submerged, the greatest depth should have been 1.5 meter plus 3 meter, which is 4.5 meter. That is, if the free surface, and this is the circle, and the diameter is 3 meters, so this is radius is this diameter is 3 meter, and the least depth is said to be 1.5 meter. If indeed it was vertically submerged, then the greatest depth should have been 4.5 meter. However, the greatest depth is given to be 4 meter and not 4.5 meter, which means that this is wrong. It is indeed inclined to the free surface, and that's what we should be understanding. And so we'll redraw the figure as an inclined plane surface. The least depth is 1.5 meter and the greatest depth is 4 meter below the free surface, and angle is unknown, so I'm going to mark it as theta. Now the diameter is given as 3 meter. The distance of G and P below the free surface is h bar and h star respectively. This is 1.5 meter, which is the distance from the top surface to the centroid, which is the radius of the plate. This is also 1.5 meter because the total diameter of the plate is 3 meter. This distance is unknown, so we will mark it as x. Now we will use our knowledge of simple trigonometry to solve this problem. From the figure, sine theta can be written as 1.5 by x, which can also be written as h bar divided by 1.5 by x, which can also be written as 4 divided by 3 plus x. So using these three equations, you will be able to find out the value of x as well as h bar. So 1.5 by x is equal to 3 plus x. We will be able to get the 1.5 by x is equal to 4 divided by 3 plus x. We will be able to get the value of x as 1.8 meter. Once we get the value of x as 1.8 meter, we will be able to find out the value of h bar by substituting 1.5 by x is equal to h bar divided by 1.5 plus x, and h bar we will be able to get as 2.75 meter. Once we get the value of h bar, finding out the remaining is very simple. Ig is equal to pi d raised to 4 by 64, which is the formula for moment of inertia passing through the centroid of a circular area. So we will get Ig to be 3.976 meter raised to 4. Total pressure force is given by rho g h bar into A, which is 1000 into 9.81 into 2.75 into pi r squared, which is pi into 1.5 squared. Area of the plate is pi r squared. Substituting, we will get total pressure force to be 190,692.71 Newton, or simply 190.692 kilonewton. H star is given by Ig sine squared theta divided by h bar A plus h bar. Now sine squared theta is unknown, but sine theta is given by 1.5 by x, and x was found out to be 1.8 meter. So I can simply take sine squared theta to be 1.5 divided by 1.8 the whole squared. And substituting the remaining values, I will obtain h star to be equal to 2.892 meters. Case 4 is different from the other three cases, as in it stands for a curved surface that is submerged in the liquid. So here you can see it's a beaker and it's having a curved surface, an edge of a curved surface that is filled with water, and I have to find out the total pressure force that is going to act on the curved portion of this beaker. So if I have to draw a three-dimensional view, this would be how the three-dimensional view of the curved surface would be looking. This is the curved portion and this is the cuboidal portion of this beaker. Now, considering this three-dimensional view, I will also draw the two-dimensional view of this figure. And the net force acting on this curved surface is going to be like this. It is going to have an x as well as a y component. This is the fx component of fr. I can mark it as fx on this three-dimensional figure, and this is the fy component of fr, which can be marked like this in the three-dimensional figure. So for a curved surface, we are going to find out fx and fy separately, and we are going to find out fr. Now how to find out fx and fy separately is what I'll be talking to you about next. Let us just concentrate on fx. How to determine fx? Fx is the horizontal component of the resultant force acting on the curved surface. Now to obtain fx, it's very simple. Fx is the pressure force acting on the projected area of the curved surface. So this is the curved surface, and the projected area, the vertically projected area of the curved surface, I will shade it in a moment. This is the vertically projected area of the curved surface. So if this is the curved surface, this is the vertically projected area of the curved surface, and fx is, you can compute fx like if it was this area A that was submerged in liquid. That is, you go back to case 1, vertically submerged fluid, vertically submerged surface immersed in the fluid, and fx was rho g h bar into A. So take this as a vertically submerged surface and find out fx. This is the vertically projected area of the curved surface, and so fx is given as rho g into h bar into A, where A is the projected area of the curved surface and h bar is the depth of the centroid of the area A below the free surface of water. So fx, you don't have to consider the curvature or anything. Just imagine that this is a vertical plane surface submerged in a fluid, and find out the fx for this particular area alone. That will give you the horizontal component of the resultant force acting on the curved surface, and h bar is the distance of the centroid G of this projected area below the free surface of water. So this is h bar. So fx is the pressure force acting on this projected area of the curved surface, and it is given by rho g into h bar into A. To determine fy is the vertical component of the resultant force on the curved surface acting, uh, and so Fy can be calculated as the weight of the liquid contained inside the curved surface below the free surface of water. Suppose this is the free surface of water, then the weight of all the water below the free surface contained above the curved surface will be equal to Fy. So if I want to calculate Fy, I am going to calculate this volume, let this be V1. I am also going to calculate this volume, let this be V2. So the total volume of this particular figure is V1 plus V2, and the force Fy is given by V1 plus V2 into density into G. That is, volume into density into G is nothing but mg, which is equal to weight. So weight of the fluid acting in the downward direction below the free surface above the curved surface is giving you Fy. So all you need to do is calculate the weight of the fluid contained inside the curved surface, and it will give you the value of Fy. So Fx is the force acting on the projected area, and Fy is the weight of the fluid acting above the curved surface, which can be simply found out by V1 plus V2 into rho into G, and you will get the resultant force Fr as Fx is rho g h bar into A, Fy is equal to V1 plus V2 into rho into G, and Fr can be obtained as square root of Fx squared plus Fy squared. And whenever you have an inclined force, you should also find out the angle phi, and tan phi is given as, or phi is given as tan inverse of Fy by Fx. This is how we find out the net force acting on a curved surface. So let us do a problem on the same. This is the question. Compute the horizontal and vertical components of the total force acting on a curved gate AB, which is in the form of a quadrant of a circle of radius 2 meter as shown in the figure. Take width of the gate as unity. So width is the dimension that you cannot see. It's into the plane of this screen. So that width can be taken as unity, and the dimensions, other dimensions are given. This gate is in the form of a quadrant of a circle of radius 2 meter, and above that the column of water is 1.5 meter high. Now you have to find out Fx and Fy. That is what they meant by compute the horizontal and vertical components of the total force acting on the curved gate AB. So this gate is AB. Fr is the net force acting on the gate AB. You have to find out Fx and Fy, which are the horizontal and vertical components of the total force acting on the curved gate AB. So let's move ahead to doing this three-dimensional view of the curved surface here. So this is the 2 meter diameter gate, and there is a 1.5 meter high column of water above it. And this is Fx. Fx is the force acting on the projected area, the pressure force acting on the projected area of the curved surface. So these are the dimensions. Radius is 2 meter, height above that is 1.5 meter, and the width of the gate is 1 meter. Please forgive me for the scaling. The scaling is not correct, but I've just drawn it based on the figure in the previous problem. So the width of the gate is 1 meter, and the radius of the gate is 2 meter, and above that there is a 1.5 meter column of water. This is the projected area of the gate. And so Fx is given by rho g into h bar into A. From the figure, h bar can be calculated to be 1.5 plus 1, which is 2.5 meter, and area is the area of this projected surface, which is 2 into 1, which is 2 meter squared. So from the figure, h bar is 2.5 meter and A is equal to 2 meter squared. Area, when you're talking about area, you're talking about the shaded area, that is the projected area of the curved surface. It comes to 2 meter squared. And so Fx is equal to rho g into h bar into A, which is 1000 into 9.81 into 2.5 into 2, which comes to 49,050 Newton. This is the value of the horizontal component of the resultant force acting on the curved gate, or Fx. Fx is the horizontal component. Next we have to find out Fy. Fy is nothing but the weight of the water above the curved surface below the free surface of water. So I'm going to calculate the total volume. Now I know the dimensions over here. Now the volume V1 of the cuboid is 1.5 into 1 into 2, and so Fy is V1 plus V2 into rho into G. So V1 is obtained as 1.5 into 2 into 1, which is 3 meter cube, which is the volume of the cuboid. And the volume of the small quadrant surface is area of the quadrant into length. That is how we obtain the volume V2. Area of this quadrant surface is pi r squared by 4, which is pi into 2 squared by 4, and into length is 1 meter. So area into length will give pi r squared by 4 into 1, which would give me 3.14 meter cube as V2. And so the total volume can be obtained as 6.14 meter cube, and the weight would be 6.14 into 1000 into 9.81, which comes to 60,249.02 Newton as Fy. So Fy is the total weight acting downwards. That is the vertical component of the force acting on the curved surface. Now, another question that arises is, what happens if the fluid is present outside the curved surface? Now, it's not always necessary that fluid should be contained inside the curved surface. Fluid can also be present outside the curved surface. Here it is A and B, gate A and B. Water is actually present outside the curved surface. How does this affect the force acting on the curved surface? So, answer is this. Resultant force would be acting in the opposite direction. Fx and Fy would also be acting in the opposite directions of the previous case. So here Fx and Fy are found out in the same way as if the water was inside the curved surface, and that is how we solve this problem. We will consider or assume that the water is inside the curved surface and we would solve for it. But we would reverse the directions of Fx and Fy. That is, instead of pointing Fx towards the left, Fx is now pointing towards the right. Instead of giving Fy downward direction, Fy is now pointing upwards. So we will find out Fy as if it was water was inside the curved surface, but we'll give it an upward direction. We'll find out Fx as if water was inside the curved surface, but we will give Fx the opposite direction. And that is how we will solve such problems. So here Fx would be towards the right and Fy will be towards the top, and Fx would be determined the same way, which is rho g h bar into A. Fy would be found out in the same way as V rho g, which is the total weight of water contained inside the curved surface, and Fr is square root of Fx squared plus Fy squared, and phi is tan inverse of F. Going on to a numerical problem of this type. Determine the magnitude and direction of the resultant force due to water acting on a roller gate of cylindrical form of 4 meter diameter when the gate is placed on the dam in such a way that water is just going to spill. Take the length of the gate as 8 meter. So this is the case. This is the gate. This is the water behind the gate, not inside the gate, it's behind the gate. And the dimensions of the gate are given. We have to find out the total pressure force acting on the gate. So this is the three-dimensional view of the gate. Now this is the curved surface behind which water is acting. So the projected area would be this rectangle. I'll first draw the dimensions. The diameter is given as 4 meter and the length is given as 8 meter. Now to find out Fx is given by rho g h bar into A, where h bar is equal to 2 meter, which is the half of the rectangle, the height of the rectangle, and area would be 4 into 8, 32 square meter, which is the projected area in the case of this particular figure. So A is 8 into 4, 32 square meter, h bar is 2 meter, and Fx can be obtained as 1000 into 9.81 into 2 into 32. Now, that comes to 627.84 kilonewton. Moving towards Fy, Fy can be calculated as the net weight of water that is acting inside the curved surface, as if the water was acting inside the curved surface, however with opposite directions. And so the volume of this curved surface would come to pi r squared by 2, which is the area of this semicircle, into length. And so Fy would be the weight of the fluid inside the curved surface, which is volume into density into g. Volume is area into length into rho into g. Area is pi r squared by 2 into 8. and substituting the values, we will obtain Fy to be equal to 493,104.38 Newton or 493.104 kilonewton, which comes to Fy, but Fy is acting, as you can see, in the upward direction because actually there is no fluid inside the curved surface, fluid is outside the curved surface, and though we find out Fy as if the water was contained inside the curved surface, since the water is not actually there, Fy is given the opposite direction. Now Fx and Fy have been obtained, and Fr can be found out, and also the angle phi. Without finding out angle phi and Fr, this question will not be complete. And so Fx is given as 627,840 Newton, Fy is 493,104.38 Newton, Fr is given by square root of Fx squared plus Fy squared, which comes to 798332.6 Newton, and phi, which is tan inverse Fy by Fx, comes to 38.5 degree. So this was a presentation on hydrostatic forces on surfaces. 4 different cases were presented: when it was vertically submerged, when the plane surface was submerged at an incline, when the plane surface was horizontally submerged, and when a curved surface was submerged in fluid. The formulae are very similar and quite easy to grasp. I hope that you have understood the concepts explained in this presentation. Thank you.